So I'm going to present you our comparison of low-marine cloud property between our global model EMAC and active measurements. This will be a very short talk. I will explain you in the following briefly our model, then the data we use from Activate, and explain you what we are comparing and the results of comparison. Next slide, please. Okay, so we are using a global general circulation model EMAC for our simulation. That's in the title. Our aerosols are simulated with one aerosol submodule, MED3 on the left. And this MED3 can explicitly simulate the 9 aerosol species distribute in 3 particle mixing states and in 3 different size classes. So our clouds are simulated with a 2-moment cloud scheme, which is on the right plot. And different type of clouds are simulated using different clouds parameterization. So the bottom one, Abdul, Gatska, and Gang cloud parameterization for liquid clouds is the most important one for low marine clouds as observed by the Activate. So we are using a global model, not the scale difference between global model and active measurements. Active take measurements in second interval, but our grid model has a grid box of roughly 300 kilometers, and our calculation time step is 15 minutes. We use 11-hourly outputs for comparison in this talk. So we did simulation for Activate measurement time 2020 to 2022. We use nudging to reproduce Activate condition as much as possible. So next slide, please. Basically, we use the 2 papers from Kirschler as our base of comparison. The first one consider all cloud samples measured within 3 active measurements year. We use this for our statistical comparison. The second one consider the cloud-based sample, which is taken the first observational year from Activate campaign. This takes only the clouds at cloud base, which associate with updraft velocity. And those samples shown high CDNC, the cloud number droplet values, than the mean over all clouds. Next, please. Okay, so our model outputs 4-dimensional data. We need to apply filter to collect a sample from global model to ensure the proper comparison. So by using the filter on the left plus additional conditions, we can prepare data from global model for the respective case from the active measurements to compare with all clouds event sample and the cloud at cloud base. So next. So after having data from both EMAC model and active, we are able to evaluate how good can EMAC global model simulate low marine clouds in active region. Basically, we did, to repeat here, 2 analyses. The first is the statistic comparison. We will compare multi-annual mean of CDNC value. We will compare the vertical profile of CDNC value. The next is we would like to evaluate the model cloud dynamic. We would like to see whether the global model can reproduce the dependency of CDNC on updraft velocity as has been identified in Kishler et al. 2022. Next slide. Now here we are looking at the results. Let's first have a look at the multi-annual mean of CDNC values. The left plot is our previous evaluation of model simulated CDNC against many different observation data sets as published in Ricci et al. 2020. In this plot, each dot represents one source of observation, and the area between the dashed line means the difference between model and observation are less than a factor of 2. So the gray dot there is a measurement from Dakiva. Dakiva is also a flight campaign similar as Activate. The other dots are from satellite observation. So from this plot, we see that satellite observation has large variability, at the same time also have large uncertainty. It seems like that our model agree with flight campaign better to this Dakiva observation. So we update the left plot to the active observational years 2020 and 2022, and also include activate measurements as a blue dot here. Similarly, we see also a good agreement between model and observation for this multi-annual mean CDNC value. Next slide, please. Now we can compare the vertical profile of CDNCs here. We are comparing the vertical profile from model in blue color with the active measurement in pink, the condition for winter on the left and for summer on the right. So we see here also very good agreement between vertical profile of CDNC. We see also a better agreement for winter than for summer. And next slide, please. Okay, next we move away from climatological or multi-annual mean comparison. Now we move to the level up to the process level. To recall what has been identified in Kishler et al. 2022, the plot on the right. So you see here a dependency of CDNC on the y-axis on the updraft velocity on the x-axis. And we see here also the difference in this dependency in winter and season and summer. We see also difference in this dependency between the different aerosol loads group. The higher aerosol loads on the top to the low aerosol loads on the bottom. So here we will then evaluate to check the model, whether the model can reproduce the data distribution of both variable and also to see by whether the model can reproduce this dependency of CDNC on the updraft velocity. Next slide, please. So here we are comparing the data distribution between EMAC model and the active data for updraft or velocity on the left, for CDNC on the right. We see here a very good agreement for the updraft velocity, but on the right plot we see that model underestimate the CDNC value at cloud base. Model also underestimate the data spread of CDNC value at cloud base. Next slide, please. Okay, good. Now we can include the curve from model in the dependency plot. Those two lines in blue color are from model simulation. The dark blue represents the group with large aerosol loads. The light blue represents the group with small aerosol loads. So we see here the slope of this dependency from model simulation is lower than that from the activate measurement. This is because that model underestimate the CDNC values at cloud base. But other than that, we do see that model simulate reproduce this dependency of CDNC on updraft velocity. Model also reproduce the difference, seasonal difference between winter and summer on the right, winter on the left, summer on the right. Model also reproduce this difference in this dependency from different aerosol loads group, the dark blue one and the light blue one, which means the global aerosol model capture the climate, this basic climate dynamic. Okay, next slide, please. So to sum up, we do see a good agreement between a cost global model and activate measurements for multi-annual mean CDNC values and the vertical profile of CDNC values. Model capture the cloud dynamic, but model this cost resolution model underestimate the CDNC variability. At the same time, we do see also large variability and uncertainty from different observations. And we see also the challenge in the comparability between model and in situ measurement due to different scales. That's all. Thank you.